Okay, so reminder that homework 1.2 is due on the 25th. It's on Canvas. So that involves reading the rest of chapter 1 and solving some problems. So please take a look. We'll try to solve one problem today on problem number 5. I also uploaded the dimensional analysis worksheet on Canvas. It's under files. We will do that next week. So we are getting there. We will discuss what is measurement, what is mathematics today. And then once we finish that, we are good for dimensional analysis. So that's when we will do the worksheet. And you will do the worksheet with me together. And then you will submit that as a part of your homework 1.3. So dimensional analysis would be a big chunk of your homework 1.3, right? So, and I will announce the date for homework 1.3 soon. So we'll get started with the lecture today. So we started looking at the foundational principles of physics, right? That things exist and things change. And then we looked at the principle of non-contradiction. And then we looked at the principle of causality. And then we started looking at mode of existence. We looked at substance and properties, right? Does anyone remember what a substance is? Right, something that can exist by itself. Very good, right? How about properties? Are there different types of properties that we saw? Anyone? Or how can you divide majorly? Yes, go ahead. Right, intrinsic and extrinsic. Intrinsic meaning they are inherent to the substance. You don't have to compare it with something else, right? Intrinsic to the substance, no comparison with something else. And extrinsic, as the name indicates, is comparing with something else. So what are the intrinsic properties? Yes. Quantity and quality, very good. Quantity and quality. Okay. What is quantity? Yes. Extension. Quantity is extension. Is everyone following? What is extension? Okay, go ahead.
Having one thing next to another.
Having one thing, having one part next to another, right? Having one part next to another part, extension. So extended, right? Extension is so primitive, right? If somebody were to ask you what is a part, but you cannot, you hit a brick wall at some point that you cannot describe anymore in words. You can only say, yeah, part, man. You just get it from the inside. You see, just you know it. You know what's a part, right? You see what I mean? Right? Extension, you know it, right? So we're starting from there. These are the primitive facts. That's where we're beginning from. That's what we know. You cannot go deeper than this. You cannot go more basic than this. Right? So quantity has to do with extension. So quantity is not just number. We'll see what a number is coming up. It is extension, having one part next to another. Can you imagine any physical thing without extension? Any physical thing without quantity? Right. You can imagine a physical thing without certain qualities, right? But you cannot imagine a physical thing without extension. Any physical thing must be extended. In other words, quantity or extension is the base property. This is the base property. Like, for example, let's take that wall, right? You think about, that wall without, you think of that wall without the texture. Then sort of turn the texture off in your mind, right? And just think of the wall without the texture, right? And you can think of the wall without that pain, right? But try to think of the wall without extension. It becomes meaningless. cannot really do it. Right? So I said, turning things off. So that brings us to a very important question where we will take a little bit of a detour. We're going to discuss the word abstraction. What do we mean when we say abstraction, or when you abstract a thing? What does it mean? Abstract. Based on ideas. Okay. Anyone else? What do you mean when I want some of you are answering, some of you are silent. So I want the silent ones to answer. Okay. Kind of like randomness. Okay, randomness. We don't know what randomness is. So I'm talking about the process of abstraction. What do we mean by abstracting something out? Yes. Okay, getting there, generalizing. Okay. Saying not concrete, but very vague or more. Is that what you're implying? Not very well defined. Anyone else? So really, all these properties, when you think about a physical thing, they all exist together. They don't exist, one independent of another. It's not like extension exists independent, and then there is something else that is existing independently. But in our mind, I can think of color by itself in my mind, like as if, I can have something color independent of extension, right? I can imagine red independent of extension, right? In the sense that I can turn off some parts. I can turn off, when I think about a wall, I can turn off the hardness of the wall, right? Or when I think about a cat, I don't need to think about cat of a particular color, right? Or I think about a car, I don't have to think about a car of a particular color. I can just think about a car. So I can turn some details off, right? But those details can really not be turned off in real life. If you look at a car, it will have some color, right? If you look at a cat, it will have some color. But in my mind, I can turn this off. So I'm abstracting. I'm abstracting this thing out as if it is not there. That's what we're going to do in physics to begin with. So we're going to, when we study mechanics, we'll see that we're going to say, hey, we're going to turn off gravity. That doesn't mean gravity is not there, right? We're just turning it off. We're abstracting. We're going to turn off friction. Doesn't mean friction is not there. We're just turning it off in our mind. We're just abstracting it out. And then later on, we'll bring those things back. We'll bring gravity back. We'll bring friction back. And then study those. That's what abstraction is, turning things off in your mind. The opposite is being concrete. Concrete is what you have in reality. Okay, so we saw quantity, which is extension. So it's not just a number, it is having one part next to another. And quality is how a thing is, right? Quality is how a thing is. Can you think of some examples of qualities? Yes. Texture. Texture, very good. Color. Mass. Hardness. Okay. Temperature. I know I said temperature, but we should be more careful. Let's say hotness and coldness or heat, because temperature could be confused with measurement of temperature. So what we probably mean is the quality of being hot or quality of being cold, right? So quality is how a thing is, right? So you gave me so many examples. So one main difference between quality and quantity is quantities are always additive. Quantities are always additive. That is, if I have, let's say, I have a liter of water, I have another liter of water, I pour them together into a bucket, then I would have 2 liters, right? I have 1 meter, add another meter to it, I have 2 meters, right? All quantities are additive. You have $100, I give you $100 more, you have 200. Qualities are not necessarily additive, right? You get 100 mediocre physicists, You cannot make an Einstein out of them, right? Are you following me? Right. Right. But the key word is qualities are not necessarily additive, right? But quantities are always additive. So we will see that you can use measurements to give a quantity to a quality, but that does not reduce quality to a quantity. For example, some of you said color is a quality, right? So you could have something that's red and something that's redder, right? So you can think about giving it a scale, right? Like red is a certain intensity, redder is more intense, right? You can give it a number. Can you think about some other scale for a quality? For example, like hardness, right? How many of you know Mohs hardness scale? Right. Have you heard of the hardness scale? Okay. That's fine. So you can assign a number, but that does not reduce the quality to a quantity. Just it still doesn't tell you. If I tell you the intensity is 100, it doesn't tell you what the color is. The color is still what that color is. That's the quality. Right? How a thing is. So these are intrinsic, and then we have extrinsic, right? So there's a mnemonic to remember this. That is rare poet. Rare poet. First R stands for relation. What's a relation? I can compare two things. I can compare two physical things. I could say this thing is longer than that thing. This thing is redder than that thing. Relation. Did you have a question? Are you following me? Any questions? Then we have action and reception, that I can act on something. I can push something. I can heat water. When I push on the board here, right, the board is receiving the action. When I heat water, water is receiving that heat. That is reception. Action and reception are like two sides of the same coin. One cannot exist without the other, because if the other thing is not able to receive, I cannot really act. Right? But this reception is not reaction. Reaction is just another kind of action. Meaning, when I push on the table, if you say the table is pushing back on me, that means the table is acting on me. Table is not receiving really, right? When you say reaction, the table is acting. Reaction is an action. Reception is different from reaction, right? Notice that. Reception, this A is action, and this is reception. You receive, right? And then, so this E belongs to this RE, belongs to the reception E. Okay. And P is the place, right? And orientation, environment, and time. This is what we have seen in the last lecture. Right? You can think about place, lexical, right? I'm here, you're there. Orientation, up, down, pointing this way, that way. And then what is surrounding you, right? For example, for a fish, the environment would be water. For you, it is air, other people, right? And then finally, we have seen time, right? We saw that time is the duration of change. Time is the duration of change. It's an extrinsic property. Because change happens, change is extrinsic. Right? Because one thing must act on another thing for that thing to be changed. That's what we have seen from our foundational principles. What is change? Anyone? How did we define change? Okay, you guys have answered before. Let's give a chance to someone who has not answered. Yes. Very good. Actualization of potency. Right? Actualization of potency. That's fine. It's an extrinsic property. How about change? Is change a property? How many of you think change is a property? Would you say change is a process? Yeah? Yeah, change is a process. Change is not a property. Right? Change is a process. This will come to use later on when we go to chapter 3, right? So remember that in chapter 1, you have seen and you're convinced that change is a process and it's not a property, right? So later on, when we go to chapter 3, right, and we talk about some things, I'll bring this back. So make a mental note, right? Okay. Now let's get to this question. What is math? What do you mean by math? What is mathematics? You want to take a shot? Yeah.
Yeah.
Sorry?
Calculation.
Very good. Okay. Calculations using numbers. Okay. Calculations using numbers. Okay. Anyone else? Yes. Sorry? Language of physics. Okay. We have some poets in the class. Language of physics. Okay. So we have discussed that all our knowledge primarily comes from our senses. Not all our knowledge is not sensorial knowledge, but all our knowledge comes from senses. From the sensorial knowledge, we have our intellectual knowledge. But we get all our knowledge, the input is from our senses, right? And this is from the physical things around us. That's what we are looking at. We're looking at the physical world around us. And what is the base property of all the physical things? What is the base property that we have seen for all the physical things? Go ahead. Quantity, right? Do you all agree? There is quantity, there is extension, right? So math is really study of quantity. Here, by quantity, we don't mean number, we mean extension. What is number? Now, we said extension. Extension, we said, is having one part next to another, right? So when you have multiple parts, then you can count one part, second part, third part, number, right? You have a number of parts. But is that it? No, but each part would have a boundary, right? You have a physical thing that is extended. It not only has some parts, but these parts are arranged in a certain fashion, right? They also have shape, right? Something could be spherical, right? Something could be like a square. Something could be circular. They also have shape, not just parts, but these parts that have a boundary that has a certain shape. Some people may say shape is a quality. Some people may say shape is quantity. We'll talk about that later. But the important thing is that you can count the number of parts, but these parts also have shapes, right? So because things have shapes. Are you following me? So you can count, right? That is numbers. And then you have shape. So when you study numbers, that is when you're doing arithmetic. Right? Arithmetic is you're studying numbers. When you study shape, what are you studying? Geometry, very good. Geometry. Yes.
What is calculus?
We'll come to it. So, study of quantity, right? That is extension. Extension is you can count the number of parts, that is number, right? And parts have shape, that is geometry. And the modern part is we have connected these two things. We have connected these two things using more properly analysis. You have algebraified geometry, right? So algebraified geometry meaning how many of you recognize what this is? Okay. 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 Anything? Okay. How many of you recognize this is the equation for a circle? You have algebraified a circle. Congratulations, you understand modern mathematics. There is no number in it, only symbols. No shape in it, only symbols. That's the beauty of modern math, right? So that comes from the study of quantity. The modern part is the connection, the bridge. That is, we make use of symbols and we come up with rules to manipulate these symbols, right? That's what this algebra and analysis is, right? How you move one symbol over to another and what this, how you define what this plus means, what x squared means. These are just symbols. How you manipulate them. For example, if I were to write, x squared then would be equal to r squared minus y squared. These are just rules for manipulation of that equation, right? So that's what mathematics is. It is primarily the study of quantity, which has both number, that is the number of parts, and shape, right? It is geometry and connect both of them using algebra. So that's why it is very, very useful for studying physics, because, I wrote it down. He said, it is the language of physics. Why is it the language of physics? Why is math the language of physics? Yeah. You're just reversing the thing, right? So don't you think, like, does that make sense to you? Like, why? There must be. So when you're reasoning something, at least for me, when you're reasoning something, you have to go all the way down till you hit a brick wall. Like this primitively, like things exist kind of knowing, right? So why should it be the language of physics? Why is not Latin the language of physics? Right? Yeah. Explain. Math can be used to explain. I don't know the word explain, but why does it explain the physical world if it does? That's the question that we're asking. Why? Why is it so powerful? Excellent. Math is the study of quantity, and quantity is the base property of all physical things. All physical things have quantity extension. That is the base property. Right? So you're studying the base property of all physical things. That's why mathematics is so powerful, and that's why you call it often dubbed it as language of physics. But mathematics really does not explain the physical world. It is a tool, in the sense that this equation doesn't have a circle in it. This equation is really not a circle, right? It's an equation, right? It's some symbols, right? It doesn't explain anything, right? There is a lot more that you actually know a circle, right? You know what circle is, and then you have done some stuff, and then you have come up with this equation, and then you say it is a circle, right? So the math itself doesn't explain anything. The equation itself doesn't explain stuff. Because we are looking at the study of physical world, we're going to look at causes and effects, right? So these causes and effects themselves cannot be captured in mathematics. Mathematics cannot catch a cause. Mathematics can at best capture something like that. It cannot cannot capture the cause. Right? Are you following me? Do you see why math is so basic? Because it is the study of quantity, and quantity is the base property of all physical things. And all physical things must be extended. Right? Any questions? Yes? No? Okay. Okay, then the next question is, what is the modern scientific method? What is a modern scientific method? I want people who have not answered till now to take a shot. What is a modern scientific method? Do you want to take a shot? It's all right. Okay. I don't want to single out anyone, but I want somebody who has not answered to take a. Yeah, go ahead. Very good. So she says it's observation, hypothesis, experiment, validation. Does that summarize what you said? Okay. This is what is her answer to modern scientific method. So my question is, first let me ask, how many of you agree with this? Does it? Okay. Okay, how many of you don't agree with it? Okay, one. So, okay, undecided or don't agree with it? Okay, you're with him. So, what is modern about it? Correct. The question is what is modern science? The question is what is modern about this? Because Plato said it is good in theory. What about experiment? To read Plato's works, Plato actually says Aristotle did a lot of experiments. Right? Clearly, we won't call Plato and Aristotle modern. Right? So what is modern about this? Okay. Okay, good. We'll come to that, whether Newton really dropped apples or not. But yeah. It is not, it is sort of a cartoon image of the modern scientific method. It is not that it is wrong. It is sort of a cartoon image, meaning when you tell a child, right, you can explain it like this. But what is the real meaning? You are in a physics course in a college. So what is the, how would you say what is modern scientific method? Modern scientific method is looking at the world through the lens of quantity. That is, you're going to measure this. Right? You're going to look at the world through the lens of quantity. You're measuring things through the lens of quantity. And then, more importantly, this is the second part. More importantly, you're going to make use of symbols and rules to manipulate them, to express the general understanding that you have in some sort of mathematical forms. Right? That's a vital part of modern scientific method, that you express this. For example, you will study that Newton's second law is going to look like F is equal to dP by dt. This is the modern part. It is not that people did not know that if you push a thing, it will move. Right? They knew that. Modern part is this. That now you have taken that general understanding that you have observed, hypothesized, experimented, validated, right? People knew how arrows would land. There have been fighting wars long before Newton invented mechanics, right? They knew where an arrow would land if you shot it from here. They knew how to make bow and arrow, right? So they clearly had this understanding, but they didn't have this. That's the modern part. You follow me? So this is not wrong necessarily, but this is more like a cartoon image of the modern scientific method. This is what in the book is labeled as the emperiometric method. So the emperiometric method is you look at the world through the lens of quantity and then use symbols and then rules to manipulate these symbols. To express general understanding. Right? Are you following me? Any questions? Okay, now then let's look at what is measurement. What is measurement? Again, I want somebody who has not answered, take a shot. What is measurement? Go ahead. Sorry, numbers too? Okay, okay, yes. Describe quantity, okay. Anyone else? Yes. Very good, a relationship. A relationship. Measurement is a relation. For example, I have a ruler here, right? This has extension, right? I can use the extension of this ruler and compare it to the extension of this table and say, this table is 2 rulers long, right? And then I can make this ruler a unit, right? Let's say this ruler unit is R. Then I say the length of this table is 2 Rs. Are you following me? So when I say the length of this table is 2 Rs, what I mean is this table is twice as long as the ruler. So it's a relationship. So measurement is a relationship. It's an analogy to number. We'll see why it's an analogy to number, because when I talked about the measure here, I talked about measure of quantity, extension, but you can also measure qualities in some fashion, like we talked about color. So you could have a scale for intensity. You say, this is less intense, that's more intense, and you could give out some numbers, 0 to 100, based on the brightness or based on the intensity. And then that doesn't reduce the quality to a quantity, but you sort of assign it a number as an analogy to say that the higher the number, the more intense it is, right? But that does not, the number doesn't become the color. Are you following me? Right? So it's like this, like I could say your diet is healthy, but your diet is really not healthy, right? Diet is diet. It's just a bunch of, whatever, fruits or, pizza or whatever it is. It is neither healthy nor unhealthy. It is only healthy or unhealthy insofar as who eats it, right? That health is in you, right? So I'm making an analogy to your health and saying that diet, when I say that diet is healthy, meaning that if you eat that diet, you are going to be healthy. That's what I mean, right? So it's that, in that sense, I'm making an analogy to number here. It's not the diet that is healthy. It is you who is healthy, right? In the same fashion, I can assign a number to the intensity of color, but it's only an analogy. It does not reduce the quality to a quantity, right? And recall that qualities are not additive necessarily like quantities, not necessarily. For example, if you get 100 ice cubes, can you heat up water? 100 ice cubes would still be at the same temperature, right? They won't add up. Right? Because that coldness is a quality that would not add up. So measurement is primarily a relation and it's an analogy to number. Right? And measurement does not reduce quality to quantity. So what is primary? Knowing something or measuring something? What is primary? Do you need to know something first or measure something? Okay, know something first. Do you all agree? You have to know something to measure it, right? For example, if I ask you to measure the bazinga of the air around you, can you measure it? Yeah, you have to know what bazinga is, right? You don't know bazinga. I told you, hey, he measured the bazinga of air to be 1.789234 plus or minus 0.768. Does that tell you anything about bazinga? No. Right? So let's observe something more carefully, because here in this physics class, we're going to observe a lot of terms that we otherwise would use equivocally. And in otherwise, we would just sort of drop these terms because it becomes hard to communicate otherwise. When I say the length of this table is 2 meters, do I really mean the length of this table is 2 meters? Is length 2 meters? What is length? No, length is not measurement. That's what I'm trying to get at. What is length? What is the primary thing that you would have in your mind when I say something has length? What feeling do you get? Yes. Sorry? You're measuring now. Yes. A distance, okay. Long or short, yeah. Very good. It's extended. That's the base property, right? Something that has length is extended. It has extension, right? So that's quantity, extension. So length is extension. So when I say length is 2 meters, what I actually mean is the measure of length of this table is 2 meters. That's what I mean. But imagine talking like that. The measure of the height of this person is 5 feet 10 inches, right? It's very hard to talk like that, right? So we just say the height. But what we actually mean is the measure of the height. The height itself is extension, which is quantity. It's not a number. The minute you say the length is 2 meters, that's a relationship. That's a measure of length, right? So observe that very carefully. Distinguish between what is length and what is measure of length. By length, you mean you don't need to measure. Like somebody, let's imagine yourself to be, like the day you're born or something like that, you wake up on a distant planet with no other people around you and you see something, right? You don't know how to measure length or anything like that, but you still understand length. And you see things around you. You still have that intuitive understanding of length. Yes?
So length by itself being an extension does equality, but measurement of length is equality.
No, measurement of length is an analogy to number. Measurement is a relationship, right? So measurement is not a quality, right? Measure is comparing two things. You're comparing one thing to another thing. Like, so when I say I measured this table, I'm comparing this thing to another thing. So remember, we have quantity, quality, and relation, right? So relation is comparing two things. So measurement falls in the category of relation. Right? Is that making sense? Yeah. Any questions? So the thing I want you to consider here is we have started from very primitive facts, like things exist, and we're building up slowly from there. This is not usually done, but it's very, very important that we start from here because we have to understand what we're doing, right? And so we have built up from there and we have carefully examined what we're talking about, and we understand much better what is math, how we're going to use it, right? And what we are talking about, what the physical thing is, and what change means, and what time is. And then we have a better understanding now, I hope, of quantity and math in general and what measurement is. Now we are ready to deal with dimensional analysis. By dimension, it's nothing more than, where this falls in this thing. For example, let's say length, right? Length would be, a quantity, right? So length would be one kind of a base property here of a physical thing. For example, mass. Mass is something that is very different from length, right? It's a quality that's very different from length. So to measure mass, you cannot measure mass with something that has, something, you cannot measure mass with extension. Are you following me? I cannot measure mass with extension. I have to measure mass with mass. Are you following me there? I have to compare, when I'm comparing, I have to compare apples to apples, oranges to oranges. Right? So that's where dimensional analysis comes in, and that's going to be a very powerful technique. So that's where the worksheet will come to use. So when you go back home, I want you to take a look at that worksheet and look at the dimensions. Before we leave today, I want to talk some more about units and system of units. So we saw measurement is a relation. It's an analogy to number, right? So then, because we are all living together in the same world, right? We all need something standard to measure it, right? Because, I don't want to say I have a new, thing for, I probably should be saying things like this in the US, but because, now I have gotten converted into feet and inches and Fahrenheit, but when I came, 15, 16 years ago, and I used to see temperatures like 110, 90, 80. That used to scare me because it's like, okay, oh, Fahrenheit, okay, good, okay, you're not going to, it's like, because I was so used to Celsius, right? But anyway, we all want a standard so that, that meter is a standard, but there's a meter standard, right? A kilogram is a standard. So measurement, you have a standard. The standard is what you're calling essentially as a unit. That is, we all come to an agreement that we're going to call this standard thing. Okay? Whatever we measure, we're going to measure with respect to this. So if you go to Paris, there's a museum, there's an iridium cylinder that's actually 1 kilogram. So when you say 1 kilogram, that thing is 1 kilogram. So when you say something is 10 kilograms, you're saying it is 10 times that iridium cylinder sitting in Paris. Yes.
Yeah, I always thought about that. What happens when those cylinders get stolen or destroyed or broken? Like, what if it chips off and it's stolen?
Yeah, that's why we have institutes for standards and technology that have, we can go more into it, but that's a good question. Yes. So now they have more imperiometric systems. So they have defined, now the standard units are defined in a more vague way in terms of Planck's constant and how light travels and things like that. But maybe we'll get to that some other time. But for now, I just want to talk about units and standard. So the common standard that we agree upon, we give it a name and call it a unit, basically. Right. So there's a certain stick that we're going to call it. This is a meter, and that's a unit. That's meter. Right. And then a certain cylinder that we are going to call it as 1 kilogram, that's the unit. So by unit, we mean the standard that we're using to compare. Then we're comparing, we're using that standard to relate or to make a relationship with anything else. Are you following me? Right. So units are the standards that come from there. Right. And we will, I probably might send an article out, but there are different systems of units. So systems of units meaning you can have certain types of standards. For example, like I said, you could have meters that I could measure in meters, or I could measure in inches. I could measure in, kilograms and something else, or, I could measure in some other units. I could just pick, feet instead of meter or whatever I wanted, right? You could pick your own, like some stick that you find on the road and say, this is whatever your name is. You put your name to it and call it the standard, right? You just have to get other people to agree upon it, right? And there you go. You have a system, right? You can make a system. So the system is not something that exists really like a tree or like a dog, right? It's what you make up, right? So system of units is a set of standards that you would use to measure things like length, mass, time, and things like that, right? That would fall into the list of properties that we have seen, right? A system is what you would make up. So dimensional analysis is related to this. So starting from page 20, read up from page 20 for Monday's lecture, and then go to the dimensional analysis worksheet, and then I'll see you on Monday. Okay, thank you.